We are going to start our lesson back on the naming acid sheet because I know we left off with some of that lesson incomplete. So let's start with our ionization concept, which is on page 32 of your notes packet. Okay, so here we go. So ionization. So ionization occurs when we are looking at acids. Uh, so acids again are anything that contains a hydrogen ion at the beginning, and they are aqueous, which means they are dissolved in water. So they are very similar to dissociation equations in the fact that we need to show the fact that it is splitting up in water or the ions are separated within the water. So we're going to do the two we tries on this page. So we have hydrogen fluoride. So this is showing an ionic compound because if it said the acid name, it would have the word acid in it. But remember from the previous lesson on naming acids, we can change the terminology or the ionic name to the acid name by using the conversion table in your data booklet. So again, hydrogen fluoride. So hydrogen has a +1 charge, fluoride has a -1 charge, which then means that we only need one of each of the ions in order to make hydrogen fluoride. So what we have here is HF. Now we always put AQ at the end. And now we need to show the fact that it is ionizing in water or separating into its ions within the aqueous solution. So that means that we have our two ions, which are H positive 1 or H positive either or. And then you put aqueous, as you did with your dissociation equations. And then F minus, also with aqueous at the end. You must make sure that your ions are balanced. Okay, so you have one hydrogen on the product side, one hydrogen on the reactant side, one fluorine on the reactant side, and one fluorine on the product side. So we know that our atoms are balanced, and then you must look at your charges. So our charges on the product side, which again is your right-hand side, is a +1 and a -1, which will equal a 0. And then on your reactant side, which is your left side, there is no charge, which is a charge of 0. So that means that our charge is equal. You must make sure that both your atoms and your charges balance each other. Now, our second one is hydrogen sulfate. So if you don't remember what the charge is for sulfate or what it is, 8 is a big signal to you that it exists in this polyatomic table. So sulfate is right here, so SO4 -2. Hydrogen is H, and since it's at the beginning, we use the +1, not the -1. Okay, so we're using H +1 and then SO4 -2. So I know by looking at that, if I have a -2 and I need to balance it out, I need 2 of those hydrogens to balance it out. So when we put it in our formula here, hydrogen is a +1, sulfate is a -2. So that means I need to add one more hydrogen ion, and forgive me if it's not super clear, it's really hard to write on this little tablet thing I have. So that means that I need 2 hydrogens per sulfate. And remember, we are aqueous because we're looking at an acid or a acid forming substance. Now, my two ions that exist. My ions that exist are H positive, aqueous, plus my sulfate ion, which is SO4 -2. And then we put our aqueous in as well. So again, we must make sure that we balance our atoms and our charges. So right away, if I look over here on the products or the reactant side, sorry, I have 2 hydrogen. Here I only have 1. So I need to put a 2 in front to balance out my hydrogen ions. I have one SO4, or I can look at it separately. I have one S on the reactant side, one S on the product side. And then over on the reactant side, I have 4 oxygens. On the product side, I have 4 oxygens. So that's balanced. Okay, or you could look at it as an SO4. I have one SO4 on the reactant side, one SO4 on the product side, so that balances. Now your charges. On the reactant side, there is no charge. Remember, your charges are superscript. Okay, so they're found higher, not lower like you see in the formula, okay, at the beginning, but superscript higher up. Okay, so our charge of our reactant is 0, our charge of our product. In my hydrogen ions here, okay, so when I look at my hydrogen ions here, it says a +1, but I have 2 of them. So that means I have a +2. Then going to my -2, I only have 1 of them. So a +2 and a -2, that equates to a charge of 0. Whereas over here, my charge is 0. So that is our balanced ionization equation for both hydrogen sulfate and hydrogen fluoride. Okay, now we're going to skip ahead and we're going to do some of the examples because we did some of those names on our lesson for naming acids. So the U-try, so you should be able to complete some of these already based on the fact that you did the first chapter, which was solutions. So you know your dissociation equations. So it says indicate if the following would ionize or dissociate in water and show the corresponding reaction. So you have to first decide if you're looking at ionization or dissociation. So remember, ionization, you are looking at an acid or H at the beginning, okay? So that being said, let's look at A. We have copper 1 chloride. So your first step is to write the formula because the formula is not given to you. So you spent your last lesson doing practice questions on naming acid bases, ionic molecular compounds. If you did not do that and you struggle with that, you need to make sure you come see me. That is on you. So we have copper 1 chloride. So the fact that it says we have copper tells me that I have a metal, or technically a cation. Okay, and a cation, okay, I need to get back up here and I need to get a pen. Okay, it tells us right here that copper is a +1 because this Roman numeral tells me which charge I used of copper. Now, chlorine, if I go down to my data booklet, chlorine is found right here. So it is number 17. It doesn't tell me my charge, but I know according to Unit A that it has 7 valence electrons. The fact that it has 7 valence electrons means that it's not balanced because we need to satisfy our octet, which means that it needs to gain 1 more electron to become stable, and electrons are negatively charged, so by gaining 1 extra, you have a -1 charge. So going back to, I now have, that's supposed to be a -1. Again, forgive me for the messiness. So we have a +1 and a -1. So that balances out. So my formula should be CuCl. I used a +1 and a -1. But looking at this, I have CuCl, ionic compound. Doesn't start with a hydrogen. So is this ionization or dissociation? Okay, we know it's not ionization because it doesn't have hydrogen at the beginning. For dissociation, if it's an ionic compound, you must make sure that it is an ionic compound that actually dissociates or dissolves within the water. So this is where you go to get your data. You go back to your data booklet and go to your solubility chart. So your solubility chart is here. So you had Cl, one of them, so we're in this column. Then you cross down, could be in most, but double check if your other ion is here. Cu+1 is here, therefore it is very, like some of it will dissolve, but very little. So we assume that it does not dissolve. So when we write our dissociation equation, we write CuCl. And remember, we always start with a solid for an ionic compound. And then, since it does not dissociate, we show that by saying it stays as a solid when we throw it, sorry, that's supposed to be an S, when we throw it in the water. Okay, so this one was dissociation. Okay, and it does not dissolve in water because it is an insoluble ionic compound. Now my next one is H2SO4. So this one should be fairly easy for us because we just did it on the first page. So that being said, it starts with a hydrogen. So since it starts with a hydrogen, we're looking at ionization. Okay, so we write down what our compound is that we start with. Since it is an acid, we put AQ. The two things that acids always dissociate into, always, is a hydrogen ion. It's just dependent on how many, and then some sort of an ion. So the only thing that is left in H2SO4 is SO4. So I have to have SO4 located here. I know it's going to be a negative charge, and if I don't know if it's a -2 or a -1 or a -6, then I just go back to my solubility chart. Or sorry, not my solubility chart. I could go to my solubility chart, but I'm going to go to my polyatomic table here. So SO4 has a -2 charge. So now I can put my -2 charge here. Make sure that you balance it and you put your states. So I know AQ over here, AQ, and then I have H2SO4 to start with, but then I only end with one H, which means that I need to put a 2 in front of my hydrogen ions to balance out both my charges and my ions. Okay, going down. C and D. So I'm just going to talk about them and then I'm going to get you to practice them on your own. So for C, it says I have hydrogen nitrite. Okay, so the fact that I have hydrogen at the beginning should tell me that I am in an ionization reaction. So this is going to look very similar to B. And then D doesn't have hydrogen. So then I would be looking at my dissociation rules. Oops, sorry. So that being said, I have manganese 2 chloride. So that's an ionic compound because I have a cation, manganese 2. So then you use your solubility chart. Chloride. So go to chloride, Cl. Manganese could be here. Mn is not here, so I know that this one is soluble and it will dissociate. I'm actually going to do this one with you because this was a bit of a struggle in chapter 1. So manganese is a +2 charge. Chloride is a -1. So I need one more chloride to balance it out. So that means I get MnCl2, and I am solid to begin with. And then I need to show that I dissociate into my ions because I am a soluble ionic compound. Okay, so I get my 2 ions that I dissociate into, and then Cl- or Cl-1, and aqueous. Balance out your charges, balance out your atoms. So I have on this side 2 chlorines. You can see my little pen marker thing down at the bottom. But over here I only have 1. So I'm going to put a 2 in front to balance out my chlorines. I have 1 manganese, a charge of 0, a +2, and 2 of the -1s. So I have a -2 and a +2. So that equates to a 0. Okay, so we are now going to move on to the next lesson. So I'm going to skip ahead a little bit here. Forgive me if this is a little bit slow, but this is the best way I can do it. You need to be doing this table on your own. So now we're going to acid-base theory. So I am going to be teaching quite a bit today, so it is going to be a longer video, and a lot of it is new stuff for you, so at least this video will be available to you after the lesson. So acid-base theory. So science is ever evolving. For Chem 20, we are only touching on a very, very small portion of acid-base theory, which will be built on in Chem 30. And so this is one chapter that really carries over into Chem 30, because the theories that you'll learn this year will be built on and expanded in Chem 30. So if we delve into the evolution of acid-base theory, we actually start with Arrhenius, or Arrhenius. I don't know how you want to say it, but Arrhenius proposed that when certain substances, whether they be acid or base, will break apart in water, they form ions, producing a solution that conducts electricity. We do know that things dissociate, okay, and ionize based on all of our previous lessons. So now we just need to take those lessons and relate them to the acid and the bases theory to what Arrhenius is saying. So I have put down here our two definitions of Arrhenius acid and base. Okay, so you're going to want to highlight this. I'm going to try and get my highlighter out. Okay, so highlighter. So Arrhenius acids. So what Arrhenius stated, at least at the beginning, was that acids contain a hydrogen ion that would ionize, okay, into hydrogen ions and another ion. So that would be your anion. So what this means is it's going to increase the hydrogen ion, and then anytime you see those square brackets, I can't change my pen super quick, but square brackets mean concentration. Okay, so if you see square brackets, it means concentration. So when Arrhenius stated that acids would ionize or separate into that hydrogen ion, what that would mean is the amount of hydrogen ions that exists within the solution would increase, which is what he's talking about here. So it increases the concentration of hydrogen ions within that solution. And this is referred to as ionization. So this is everything that we just did in those couple of examples on the previous couple pages. But Arrhenius's bases. He said at the beginning that bases contain a hydroxide ion. And according to your lessons in grade 10, you would have talked about acid and bases very similar into these terms, containing a hydroxide ion and containing a hydrogen ion. Okay, so if it had an H at the beginning, it was an acid. If it had an OH at the end, it was a base. And that was what you learned in grade 10. In reality, that's not exactly what acid and bases are, but it's the beginning to the theories that, to what we believe today to being acid and base. So his first theory of bases was that they are going to dissociate because it's not an acid. So it'll dissociate very similar to our ionic compounds. So they're going to dissociate into a hydroxide ion and then another ion. But we should know by now that a hydroxide ion is a negative charge. So the only other ion that you have to have is a positive ion. So what it would really mean is a hydroxide ion plus a cation, because you need that positive with the negative. Okay, and what this is going to do is it's going to increase the hydroxide ion concentration within the solution because it is separating, it is dissociating into that that hydroxide ion and that cation. So this is a form of dissociation, and this shows us that bases are made from ionic compounds. So I really do want you to put in the fact that these square brackets mean concentration. So I'm going to put a square bracket equals concentration. Okay. So let's do some retries, and then there'll be a couple where you can do on your own. So we're going to start with number 1, but I'm going to scroll down a little bit so it's easier to see. So we have hydrochloric acid. Okay, so now we're tying quite a bit of our knowledge together because you have to write your formulas first. So the way to write your formulas for acids is convert the name back to its ionic name. So that being said, if you don't know what the rules are, go back to your data booklet. Sorry, I forget what page it was on. Okay, page 5. It has your acid-base rules. So hydro-blank-ic acid, which is what we have, hydrochloric acid. We're going to get rid of hydro, put hydrogen. We're going to get rid of ic acid and put I. So now we have, instead of hydrochloric acid, we have hydrogen chloride. Okay, so I encourage you to cross off the ic acid, change it to I, and then change the hydro to hydrogen. So I have hydrogen chloride. Hydrogen is a +1, chloride is a -1. So to write it, you get HCl. Since it's an H at the beginning, we're going to put aqueous. Okay, and I know this one to be ionization because I have an acid. Okay, now in my ionization reaction, I know that I'm going to ionize into my hydrogen ion, which is H+1 aqueous, plus Cl -1 aqueous. So there's my ionization reaction for hydrochloric acid. Okay, my next one is sodium hydroxide. So sodium hydroxide. So this one is going to be a base. So I need to show it as a dissociation equation. Okay, so dissociation, this one was an acid, so I show ionization. This one is a base, so I show dissociation. So sodium hydroxide, you name it like a normal ionic compound, a +1 and a -1. So I get NaOH, aqueous. Okay, so now when I dissociate them into their component ions. Na is a group 1 ion, which is soluble in everything. So I know Na positive, aqueous, plus OH minus. And then we put aqueous. That balances out because we have a +1 and a -1, which equates to a 0. There's one of every atom, so we are happy. Okay, my next one is ammonium hydroxide. So hydroxide tells us that we are a base. So this is a dissociation equation. Ammonium is a polyatomic ion, so you can look back in your data booklet, +1. Hydroxide is a -1, so I need one of each. So I get NH4OH, aqueous. Okay, and this one is also NH4 is aqueous with everything. So that means it's going to separate into its component ions. So my two ions are NH4 plus aqueous plus OH minus aqueous. Okay. So magnesium sulfate I'll leave for you. The next one is sulfuric acid. So what I'm going to do is simply come up with a formula with you for this, and then I'm going to expect you to do this one on your own. So sulfuric acid. I don't know it. Let's go to our data booklet. So we go to page 4, sulfuric acid. So it doesn't have a hydro, so it's not number 1, so it has to be number 2. So ic acid changes to 8. Now, remember I said in the previous video that sulfur and phosphorus are 2 exceptions to the rule, okay? So sulfurate, okay? So technically what we would do is cross off this and write 8. And then you put a hydrogen at the beginning. Okay, so I have hydrogen and sulfurate, but sulfurate doesn't sound right. Okay, so it is one of our exceptions to the rules, and it's just sulfate. So now I have hydrogen sulfate. Well, according to our rules, you now just name it like you would an ionic compound. Hydrogen is a +1. Sulfate is an SO4 -2. So I need 2 of those hydrogens. So I would get H2SO4 and then AQ. And then you can finish the rest of this one on your own. Okay, so there are always limitations to pretty much everything in chemistry. So that being said, this theory or this theory of Arrhenius doesn't include all of the bases. So not all bases actually contain a hydroxide ion as part of their formula. So he seemed to have just left that out. Some neutral substances also have basic properties like ammonia. And then hydrogen doesn't, or at least the hydrogen ion, sorry, doesn't exist in isolation in an aqueous solution because it likes to combine with other things in order to be stable. So this is where we're going to go into what Arrhenius changed his theory to be to take into account some of those, I guess, limitations in his first theory. Okay, so I'm going to try, sorry, this is a little slower. Okay. So modified theory of Arrhenius acid and bases. So this is the new theory. This is the theory that we like to believe in today, at least for Chem 20, because in Chem 30, you're going to change this theory. Okay, so Arrhenius modified bases. So what he said for these modified bases is they're going to react with water to produce hydroxide ions in an aqueous solution. So they do so by accepting a hydrogen ion or a proton from water. Okay, so that means they're going to take something from water to, to create that hydroxide ion. So they don't just dissociate. But again, there are some rules depending on what type of base it is. So we're going to do this in baby steps. So here are my little notes for you. So if we are a soluble ionic compound, okay, then what happens is we have the dissociation equation first. Okay, so that's what you've learned so far, okay, in chapter 1. So if you have a soluble ionic compound, or yes, a soluble ionic compound, you're going to dissociate it first, just like you did in chapter 1. So here's the example. KCl is soluble, okay, so it's going to dissociate into K plus and Cl minus. Then what happens, so step 2 is the anion, the negative ion, is then going to react with water to then make the hydroxide ions. Okay, so I want you to put the negative ion is talking about the anion. Okay, and I should have really defined this in your notes as an anion rather than the negative ion because you should know. Okay, so then what you see in step 2 down here, okay, right here, so this is step 2. This would be step 2 here. This would be step 1. So 1 would be here. So chlorine is then going to react with water. Since we're looking at a base, we need to make a hydroxide ion somehow. So in order to make a hydroxide ion, you can only get it from this water because this chlorine ion doesn't have hydrogen and it doesn't have oxygen. So then that means that this water has to do something to become an OH minus. So it's saying that we need to allow this water to donate or give something to this chloride ion to become hydroxide. So what really happens is the hydrogen ion, at least one of them here, will go to this chloride ion to become HCl, which is an acid, and then OH negative, which is now aqueous, and this shows us that we have a base. Okay, now the next one is, okay, I'm trying to get back to my highlighter, sorry. Okay, my next one here is an ionic hydroxide. So an ionic hydroxide is simply talking about an ionic compound that has hydroxide. So sodium hydroxide, strontium hydroxide, gallium hydroxide, anything with hydroxide is talking about an ionic hydroxide. So in an ionic hydroxide, you are going to show the dissociation reactions. That's it, just the dissociation reactions, as it is a strong base. We are going to talk about this later, but I put it here because a lot of students struggled with this concept. The first couple of rounds I went through uh, acid and bases, so I put it here as explanation to help. So again, soluble ionic compounds is a two-step problem. You have to dissociate first, and then you have to show the water giving a hydrogen to the anion. If you have a hydroxide, then it simply dissociates. Okay, now always exceptions, and this one you have to know. NH3 is a base. Okay, so it's one of our exceptions. It is a base. Therefore, what's going to happen in this one is ammonia is going to combine with water. And you're going to see it very similar to the note number 1 when it's a soluble ionic compound. Okay, and it's going to just do this second step. Okay, so the hydrogen will donate to the ammonia. We'll do one example. Okay, now going down, 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 down. Okay, so my Arrhenius modified acids. Okay, so Arrhenius modified acids, they are going to react with water to produce a hydronium ion. So my whole hydronium ion, memorize this, is H3O plus. So when you have these acids reacting with water, they're going to form this this hydronium ion. Sounds very similar to hydroxide, but be very careful. Hydronium is H3O plus, hydroxide is OH minus. Okay, so these guys become proton donors. Okay, so they're going to give up hydrogen ion. And this concept that you're learning right now is very, very similar to what you would learn in Chem 30. They just changed the name a little bit. So, and the reason this is happening is because the hydrogen ion cannot exist in water due to its extreme positive charge, and water molecules are polar. So we know that water molecules are polar according to our first unit. So that means that they have a slight positive side and a slight negative side. So what's going to happen is when you do make that hydrogen ion in water, it's going to immediately react with a water molecule, okay, forming that intermediate step of the hydronium ion. So we're going to show what happens when we have this hydrogen ion reacting with water. So I'm going to show it first in reaction form, and then I'll try to make pictures. So we have a hydrogen ion reacting with water, which is H2O. So our hydrogen ion is then going to be donated to this water molecule because this water molecule is going to attract it. So now instead of having 2 hydrogens, we're going to have 3. Okay, and water was neutral charge to begin with, so that means I now have a plus charge on this side. Okay, and this is okay to have a positive charge. So up until now, we've had 0 and 0 on both sides, but I'm still balanced because on my reactant side, I have 3 hydrogens and 1 oxygen, 3 hydrogens and 1 oxygen. My overall charge on this side is +1, and my overall charge on the product side is +1. So that balances out. So if I were to draw it, so this is representing my hydrogen ion. And then I'm reacting it with a water molecule. So that's going to be my oxygen. And this will be my 1 hydrogen. And here's my other hydrogen. Doesn't have a charge, which is why I don't have a charge up top. Now what I get is a polar molecule. Now this polar molecule actually creates a triagonal, sorry, no, pause for a second. It's gonna create, sorry, focusing really hard here. Our molecule in which we have our triagonal pyramidal. If you remember back to unit A. Sorry, also going on very little sleep right now. So we're going to do a couple U tries, and then we will move on. I just need my thing to pop up on the side here. So we're going to go down. So our we tries. So I've got a couple here, and it's very, very important that you practice this because we're going to build on it in every lesson. So it says, write a chemical equation to show how the following acid and bases would react in water to according to the modified Arrhenius theory. So now we're not just doing Arrhenius, we're using modified. Okay. So our first one, we have HF. Okay, so this is hydrofluoric acid. Okay, so I know that I have an acid, okay, because I have an H in the beginning, AQ at the end. So now I have to use my rules for my modified Arrhenius. So what I'm going to do is I'm going to write my HF out again. It is aqueous now. But now instead of just ionizing, I'm reacting with water, which makes H2O. Okay, so I have H2O. Now, H2O, you can put as a liquid because it is a liquid. Technically, it's aqueous too, but you can have it as a liquid. Liquid or aqueous is a-okay by me. So now we know, according to modified Arrhenius acid theory, is that acids donate a hydrogen ion. They only donate one at a time. So if HF donates one hydrogen ion, then all that's left is F. But if I look over here, I don't have a charge. This is a charge of 0. So my bank account is at 0. Now this hydrogen ion I know is positive. So pretend it's a positive 1 and you just spent $1 and your bank account was at 0. What's your bank account at now? So if you spent $1 that you didn't have, you're at a -1, which makes sense because the fluorine ion is a -1 charge. Okay, so now you put aqueous plus. Now that hydrogen ion has to go somewhere, which means it has to go to my other compound, which here is H2O. So if you gain an extra hydrogen ion, now you're H3O. And again, look at your charges. That's a perfect O. So you have a charge of 0 right now. So your bank account is at 0. You just gained a hydrogen ion, which is a positive charge. So if you've gained a positive charge and your bank account was at a 0, you only gained 1 positive, then your bank account is now sitting at a +1. Okay, always put aqueous. There you go. That's how acids, modified Arrhenius acids, will ionize. Okay, my next one. I have NaHSO4. Do you have an H at the beginning? If your answer is no, then what you need to do is, or sorry, let me just backtrack for a second. If you see this or if you see a compound like this, any compound, any ionic compound, your first step that you have to do is dissociate. First step, okay? So unless it's an ionic hydroxide, which it's not because I don't have hydroxide. Okay, so my first step will be to dissociate. So step 1, ionic compounds, dissociate. Sorry, it's messy. Okay, so step 1. What I need to do is write out my NaHSO4. Now, I'm going to put a solid because it says solid there. Okay, so now I need to double check if I can dissociate. I know that I can because Na is a group 1 ion, and all group 1 ions are soluble except for these few, which is not one that we have. So that means we're happy and we can dissociate. So now we get Na positive, aqueous, because now we're in water, and HSO4 minus, aqueous. Then what we look at is we look at our negative charge. I'm going to change my color of my pen. Let's make it blue. Oh, that's too big, sorry. Okay, so we're going to look at our anion. Our anion has a hydrogen at the beginning and has an AQ at the end. So what does that tell you? Okay, so hydrogen at the beginning and AQ at the end tells us, oops, not base. I don't know why I'm writing that. Tells us that we're an acid. So this leads us to step 2. So now, step 2. We're going to use our modified Arrhenius rules, which would be add H2O to acid. And my acid component is the HSO4 minus, so aqueous. Oh, sorry, plus. This would be a lot quicker if I had the smartboard. Okay, so plus H2O. There we go. Okay, so according to Arrhenius's modified acid rule is acids donate. So my acid is here. So acids are going to donate. So they only donate one hydrogen at a time. So then what I have left, if that gets donated and moves over here, I should get SO4. Now look at your bank account. My bank account was at a negative right now. I just lost another positive. So if I lost another positive and I'm at a -1 already, then what that would mean is I'm now at a -2. Okay, and then we have aqueous plus. The hydrogen ion has to go somewhere. So that H2O will become H3O, and then we have the plus symbol. Okay, and the reason why, not just because all acids have a hydronium ion, but because here, this water had no charge. It was a charge of 0. Bank account was at 0. And you're adding a hydrogen ion, which is a positive. Your bank account is now at a +1. Okay, so then we have aqueous. So you can double check your balancing, but that one should be balanced correctly here. And I just forgot to put my state of liquid or water, or you could put aqueous, doesn't matter for that one. So if I count out my hydrogens on my reactant side, and I'm using my fingers to count, that's fine. So I have a total of 1, 2, 3 hydrogen ions on my reactant side. On my product side, I have 3. We're happy. Okay. I have 1 S on my reactant side, 1 S on my product side. I have 4 oxygens on the HSO4 minus plus the 1 on the water. So that's a total of 5 oxygens. Make sure you have 5 on the product side. 4 with SO4 and then 1 with H3O plus. Total of 5. So hydrogen or my atoms balance out, which would mean that my ions should also balance out. But if you want to double check on your reactant side here, I'm going to try and get my highlighter. On my reactant side, I have a -1 and a 0. So that would equate to a -1, which means on my product side, I should have a total of -1. I have a -2 and a +1. So that +1 would get rid of one of the minuses here, so I would have an overall -1 charge. I'm done. That's balanced. Okay, so pen back here. Now we're going to go down. Sorry, so, okay, number 3. Okay, number 3. Number 3, if we look carefully, sorry, H2SO4. So for H2SO4, it tells you right at the beginning that I have an H. Bingo. Sorry. Okay, so I have an H at the beginning. I actually have 2 of them and an AQ at the end. So right away, that's telling me I have an acid. Okay, so then that means that I need to use my Arrhenius acids. This one I don't need to do any fancy step one because it's already in an acid form. So that means that I'm going to write H2SO4, have my aqueous, added in the presence of water, which is H2O. Acids donate. Okay, now how I remember that is acid donate. D ends in a D. Sorry, I tried to underline just the D's. So ends in a D, starts in a D. Acids, acid, donates. I feel like I'm doing a Zayden thing. Okay, so in this case, the hydrogen ion from the H2SO4 is going to be donated to the water molecule, but again, only one at a time. You can only donate one hydrogen ion at a time. So now I have HSO4 because I can only have one being donated. So my bank account was at 0 to begin with. I lost one positive. I spent $1 I didn't have. So now I should be at a -1 or just a negative. Okay, don't forget your states. I already forgot my state over here. Liquid plus. Always your other one should be H3O plus when we're looking at acids. Okay, bank account was at 0. You added an extra hydrogen, so therefore it should be a +1. So this is actually a two-stepper. You notice how I left a lot of space? Now the reason being, I'm going to just get my highlighter back again here. Highlighter. If I notice here, I still have a hydrogen. So technically this is an acid. So what this means is this next, or my formation of my acid here is also going to ionize. So I'm kind of teaching you everything in one day, but I just haven't defined it as such. Okay, so what this means is now I have to do another step, and this HSO4 minus is also going to ionize, which means I need to add it in the presence of water. Okay, it does the same thing. So this would be step 1, this would be step 2. Acids donate. So what's acting as my acid is this HSO4 minus. Okay, it's not as strong of an acid as this beginning one, but this is still an acid. So if this acid donates one, what's left is SO4, and now my bank account was at a -1. I just lost another $1. So now I'm at a -2, and we put aqueous. Okay, plus. Always ends in H3O plus aqueous. Technically, it doesn't matter if you put the H3O first or the SO4 first. It doesn't matter as long as it's on the same side of the equation. It balances out because -1 on the reactant side, a -2 and a +1 is a -1. So we're good. And all of your atoms balance out. You can count them if you so wish. Okay, my next one. So this was one that you had to memorize, that ammonia is a base. It also doesn't have hydrogen at the beginning. Okay, but this one's just easier to memorize. So what we do is take NH3. Here, it's a gas that's going to dissolve in a liquid. Oh, sorry, that's really messy. And this can happen. Okay, it just takes certain conditions in order for it to happen. So in this scenario, what we're going to have is we're going to have our water, because remember, we are going to now make a hydroxide ion. So I think about my hydroxide. HOH minus. Okay, I know I need this. Well, where does that come from? This is not the O. There's no O here. So that means that something has to be done here. So here, the water is going to donate, okay, to this NH4 plus. So bases are going to accept a hydrogen ion. So then that means that one of these water molecules, or one of these hydrogen ions from the water, is going to go to this ammonia. So then that means if it goes to the ammonia, instead of having 3 of them, you have 4 of them. So now I have NH4. Bank account was at 0. You're adding an extra positive, so you should get an overall positive charge and aqueous. Done. Okay. And this last one, you're not going to get a lot of these. Okay. Very, very unlikely. And I will give you hints that it acts as a formation reaction first. More than likely, you'll get questions like 1 to 4 rather than number 5. Okay. So that being said, formation reaction. So that means they're joining together. So in order to join these together, or you're making a sandwich, okay, you're going to combine things. So what we would have is 2 hydrogens, 1 carbon, and 3 oxygens. And this looks very similar to a pause for dramatic effect on acid. Okay, so now what you're going to do is you're going to take that acid and you're going to do what you did in, for example, question 3. Okay, so you have H2CO3 aqueous. It's going to react in the presence of water, liquid, acids donate. So then you get HCO3 minus aqueous plus, H3O plus aqueous. But did you get rid of all of your hydrogens? No. So then that means that I need to do 1, 2 of them. So now I have HCO3 minus aqueous plus H2O liquid, or you can put aqueous. Acids donate. So this hydrogen is now going to leave again. So now I'm left with CO3. I lost another positive, so now I'm at a -2. Aqueous, so I have no more hydrogen ions. So then that means I should be finished at this point now. H3O plus and then aqueous. Okay, so now what I need you guys to do is you need to do some practice. So I need you to do the U tries 1, all A, B, C, and D, and number 2, all A, B, C, and D. My subplans do say we're going to do strong versus weak acid and bases, but in 50 minutes, we're not going to do it. Okay, so just let the sub know that we're only doing up to page, whatever page number that was, page 38 in your notes package. Please have them done for tomorrow. Have a great night.